we're going to look at functions. We're going to look at functions more deeply, more closely here. And what we're going to talk about is what's called how the independent variable has to uniquely determine a dependent variable. And so what we can say for a function is that the function is given when one value of y for each value of x. Now this gets talked about a lot. Sometimes you'll see if we call the x values will be called the domain sometimes, and we'll sometimes draw a nebulous little graph of like all the little values you can pick up, and then we'll say the y values are the range, and the nebulous little values are what they can go to. And what we say is that the function is the rule that maps from an x to a y. And so that's the function. And the x can only go to one y. Now, multiple x's can end up at the same y. That's okay. But one individual x can only go to one y. I can't have this split and go off to this one. That would not be a function anymore. And so functions have this restriction where the x can only go to one y. What that does, and we'll look at the parabola that we did earlier, is it makes what's called a vertical line test. And so if we look at this value of x here, and we draw a vertical line, it can only cross the function in one place. So if I had some equation, and I'll make the equation x squared plus y squared equals 1. And if I were to go in and make a table of points for that, I would find that I get, let's see if I can actually draw this here. I always have a hard time drawing these. Okay. Yep, I see how to do this here. I think you can see the shape I'm going to get here. There we go. I get this. I get a circle with a radius of 1 about the origin. And so this is x squared plus y squared equals 1. Well, it fails the vertical line test. This value of x gives me two possible values of y. Here or here. And we can see this if I solve this equation for y only. I get y squared equals 1 minus x squared. Then I take the square root. When I take a square root, I get both the plus and the minus. And now I have two answers. And those are the two answers. There's the positive and the negative side of that. And so this is not a function. And we say it fails the vertical line test. And notice how we turned this idea of this mapping from an x value to a y value, from a domain to a range, into a visualization. That's one of our key strengths of graphs, is we can take the information we need and we can turn it into a visual. Okay, what we're going to do is we're going to put some of this together here. So we have our functions, and we have y equals x. So y equals something of x, right, some value of x. We have tables, and we can put them onto grid planes. There's a lot of things we can do here. So let's look at some neat things that come out from this, and we'll do some of the applications. So I'm looking at example 3 on page 414 in the textbook. And it says the toll to a bridge. Let me see if I can get this up here for you. I'll write it out here. So the toll on a bridge is $2.50. Commuters who use the bridge frequently have the option of purchasing a monthly discount pass. So you can get a monthly pass for $21. With the discount plan, the toll is reduced to $1. So you pay $21 for this, and the toll is now $1. The monthly cost of using the bridge can be described with the following formulas. So without the discount, so let me say, without the discount here, we'll make this in blue. So that means the cost in a month is $2.50 times however many times I cross the bridge. And this will be with the discount pass. And so it'll be, so this is saying $2.50 times each time I cross the bridge. This will be $1 times how many times I cross the bridge, but I've paid $21 up front. Now what I can do is, by making these graphs out of these, I can find when it becomes cheaper for me, how many times I ride across the bridge, to find out which plan is better for me. Right? Now let me see if I can switch through. This might take me a second here to switch. Let's see. Hey, there it came up. So here we have a graph. This is in my Desmos window. Now Desmos is an online graphing calculator. What I'm going to do here is I'm going to say y equals 2.5x. And here I get my line of how much it costs per how many times I cross the bridge. So if I cross the bridge 10 times, that would be $25. Cross the bridge 5 times, I can actually highlight the point right here and see how it tells me my answers. So 5 times it's $12.50. So Desmos is a nice utility that'll let me see what's happening. What I can do is I can now take the other equation I have, 1.0x plus 21, and if I look, something neat happens. These graphs cross at a point, and that point is 1435. What that point is saying is, and I'm going to come back over here to the other window. So we see it's crossing at 1435, so I'll come back over here. And so what it's saying is when, whoops, drawing the wrong way there. When x equals 14, y equals 35 for both of these. So let's double check that. We'll go y equals 2.5 times 14. So that's what, 35, right? Because 28, 2 times 14 is 28, plus the half, 35. Then I come over here and I'll say, okay, 1 times 14 plus 21, or 14, equals 35. So when I have to cross the bridge 14 times, these two plans will be equal. As soon as I cross more than 14 times, this will be the cheaper plan. But let's come back over here and let's look at this graph for a second. Look at that. By visually doing this, we don't even have to calculate anything, but being able to plot the two graphs, I can see my cost. And the blue graph is with the monthly payment plan. And so notice that here it's more expensive because it's higher up, because more expensive is higher up. But after this point, the blue graph is lower down, less expensive. And so this thing that Descartes did helps us solve complex problems visually. If, right, the big if, we can take the rules that make a linear function or other functions and turn them into graphs. And that's what we're going to look at the next section, is how to make linear functions and other types of functions quickly. And we're going to jump back and forth between using a graphing calculator and our mathematical functions.